So the next thing we want to look at in our study of field extensions is when are some of these objects fields and when are they not? So at the top, I'm trying to remind us of this definition. So we had Q adjoin any element alpha. So we've seen that often with a square root of 2 or a square root of 3 or a 2 to the 1/3. Things like that would be alpha. And this is defined as the smallest ring that contains both Q, the rational numbers, and whatever that alpha is. And it is all elements of this form, Q0 plus Q1 alpha plus Q2 alpha squared, dot, 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 all the way up to some nth power of alpha. And all those Q's are rational numbers. So the big question that we want to ask is when is that a field and when is it not a field? So we're going to be a little more explicit about that and say, give ourselves a new definition. So this time we're going to define if F is a field and K is a larger field. We define this F adjoin A, but with parentheses instead of those square brackets, to be not the smallest ring, but the smallest field containing F and A. So it's almost the same as what's above, except we're going to make it the smallest field, not just the smallest ring. So this is a subfield of K generated by A. Just like the Q adjoin alpha up above with the square brackets, that was the subring generated by alpha. Okay, so this is almost the same thing, except if you look at all elements of the form in this definition, now we have that same kind of thing in the numerator that we had up above, but we're also allowing any expression like that in the denominator also, and that's how we're going to guarantee it's a field. So remember the difference between a ring and a field was fields had multiplicative inverses. So they had 1 over whatever element we wanted. And so we're making this thing a field by just allowing denominators. Okay. Sometimes those expressions like this are called rational expressions in A, where the ones up above, the Q0, Q1 alpha, dot, 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 that would be a polynomial expression in alpha. Okay, so the difference is the denominators. And we have to say the denominator can't equal 0, but otherwise it's kind of what you would expect. All right, so we allow not only these polynomial expressions in the numerator, but also in the denominator. Okay, so our question now, this when is QA a field, we can phrase a couple of different ways. One way we can say it is when does Q adjoin, I'm going to write that as alpha since that's what I wrote up above, alpha equal Q with round brackets adjoin alpha. I don't think there's a language to differentiate there unless you say out the subring that contains alpha versus the subfield that contains alpha. I usually just call them both Q adjoin alpha. So when are those two things equal to each other is our question. And another way to rewrite that is when is 1 over G0 plus G1 alpha plus dot 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 all the way up to Gn alpha to the n in Q adjoin alpha with the square brackets, right? All right, so let's look at a couple cases where we know that these are the same. So for example, Q adjoin root 2, the sub equal to Q adjoin root 2, the subfield. And we know that because 1 over a plus b root 2, we can rewrite that as a minus b root 2 over a plus b root 2 times a minus root 2. We can rationalize the denominator like this. And what we get is a over a squared minus 2b squared minus b over a squared minus 2b squared root 2, where these coefficients here are in Q. And so that whole element is in Q adjoin root 2 the subring because I've written it as a rational number plus a rational number times root 2, right? So we knew that Q adjoin root 2 was a field already. Okay, another one that we know is Q adjoin root 2 and root 3 is already a field. And this was one you did for homework, so it was chapter 2, number 8 in the textbook. Okay, so that's another place where this was already a field. You learned how to rationalize that denominator in that problem. All right, then that is a non-example. Q adjoin pi is the same as Q adjoin pi, the subfield, okay? Because 1 over pi is not in the ring. Which, another way to say that is that 1 over pi does not equal some q0 plus q1 pi plus q2 pi squared, dot, 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 up to q n pi to the n for any rational numbers qi and any n that's a natural number. So 1 over pi cannot be written in this way. Pi is special, so you know it's irrational, but root 2 is also irrational. Pi is different from root 2 because pi is something called transcendental. And we'll define that in just a second. But pi can't be written as that expression up above in powers of pi. 1 over pi cannot be written as an expression, a polynomial expression in pi. Another way to say this is it's not the root of any polynomial with rational coefficients. Rational. And this is different from something like root 2. So root 2 is the root of x squared minus 2. And this is part of why we call this the square root of 2, is because it's the root of a squared polynomial. Okay, and so that's one of the big distinguishing differences between something like root 2, which is irrational, and something like pi, which is also irrational, but even weirder than root 2. All right, so let's see what our definition is here. Okay, so if we have a field extension, so K and F are fields, F is the smaller field, K is bigger. Any element A in K is called algebraic over F if we have this expression f0 plus f1a plus f2a squared dot dot dot, that we can make that equal 0 for some natural number n and some coefficients that are in F, the smaller field. Okay, so A is algebraic if we have this expression equal to 0. Another way to say that is that A satisfies a polynomial, so it's the root of a polynomial with coefficients in F. Okay, so that's what it means to be algebraic. It means you're the root of a polynomial with coefficients in F. And if you're not, then you're called transcendental. So transcendental means you don't satisfy a polynomial with coefficients in F. Okay, so for example, root 2 is algebraic, root 3 is algebraic, 2 to the 1/3 is algebraic, 3 to the 1/4. These are all algebraic numbers because over Q, because they all satisfy a polynomial. They're all the root of a polynomial with rational coefficients. Here are the polynomials. X squared minus 2. Root 2 is the root of that polynomial. X squared minus 3. Root 3 is the root of that polynomial with rational coefficients. For 2 to the 1/3, that's the root of x cubed minus 2. That has rational coefficients. 3 to the 1/4, that's the root of x to the 4th minus 3. Okay? But pi and e are transcendental. So they are not the roots of polynomials with rational coefficients. Okay, so I want to point out this correspondence that's in this definition, this correspondence between an expression with powers of a and a polynomial. That's going to become useful to us, and that tells us where we're heading in our next chapter. So let's look at that correspondence a little bit. So we had that expression f0, f1a, dot, 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 up to fn a to the n. That's a polynomial expression in A, and that's corresponding to a polynomial, f0 plus f1 plus dot 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 plus fn x to the n, a polynomial with the variable x. So one way to think about it is you're taking that polynomial, you're plugging a in to get that correspondence. And moreover, if we have this f0 plus 1a plus dot 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 plus fn a to the n, if that equals 0, that tells us that a is the root of that polynomial, which is going to be a useful thing to do. So, and we can do this either way. If we know a is the root of a polynomial, it means we get this expression set equal to 0. And remember, that expression set equal to 0 says something about a set of vectors, 1a, a squared, up to a to the n. This expression being equal to 0 says those are linearly dependent. And that's going to be useful to us also. All right, so we're taking these polynomial expressions in A, these things that we've been seeing and dealing with, and we're turning them into polynomials. And so chapter 5 coming up is going to be on polynomials. So some of it will feel very familiar and parts of it will be somewhat new.